So what if I told you that the forward march of time, the very thing that seems to govern our entire lives, might not be fundamental at all? What if it's just an emergent property, like an echo of something much bigger happening in a higher dimension? Well, that's the wild question at the heart of a radical new idea called the time-force hypothesis.
Look, physics is kind of haunted by a few really profound mysteries. Let's start with the big one, the arrow of time. All our fundamental laws, from gravity to electromagnetism, they work just as well forwards as they do backwards. So why do we only remember the past and not the future? Right? Why do eggs break, but they never ever unbreak? It's a puzzle we've honestly never really solved.
Then there's mystery number 2, the expansion of the universe. We know for a fact it's getting bigger. We see galaxies flying away from each other all the time. But why? The Standard Model, our best description of the cosmos, it tells us that it's happening, but it doesn't really explain the deep, fundamental force that's driving it all.
And the third big mystery is quantization. When you zoom way, way down to the smallest scales, everything, energy, matter, you name it, it comes in these tiny, indivisible packets, these little quanta. Why? Why isn't the universe just smooth and continuous? Why does it have this kind of pixelated nature at its very core? It's a rule we just have to tack on to our theories, but we don't know the real reason for it.
Okay, so we've got 3 massive and what seem to be totally unrelated questions. This is where the time-force hypothesis, or TFH for short, comes in. It proposes a single, unified answer to all of them. It's suggesting that these aren't separate problems at all, but just different symptoms of the very same underlying cause.
So here's the absolute core of the idea. The TFH claims that time, as we experience it, isn't a fundamental part of the universe. Instead, it emerges. It's what we see when our 3-dimensional universe is losing energy into a 4th spatial dimension. Think of it like the heat radiating from a cooling engine into the air. That flow of time we feel is just the signature of our universe settling down into a lower energy state.
I know, it's a pretty wild idea. So to even begin to see how it could possibly work, we need to completely reimagine our universe. We have to stop thinking of it as a self-contained system, and instead picture it as just one slice of a much larger 4-dimensional reality.
And this right here is the fundamental shift in thinking. Standard physics gives us a universe with 3 dimensions of space and 1 of time, right? 3 plus 1. And in that universe, energy is strictly conserved. It can't be created or destroyed. The TFH model, on the other hand, proposes a universe with 4 spatial dimensions. Our entire 3D reality is just a kind of membrane, what physicists call a brane, that's floating within this bigger space. And what we perceive as energy being lost over time, well, that's just energy literally leaking from our brain out into that 4th dimension.
The paper where this idea comes from frames it perfectly. This process of things running down or cooling off, what physicists call damping, it isn't a true loss of energy from the whole system. They call it a geometric flux, which is just a fancy way of saying it's a physical flow of energy out of our visible dimensions and into that hidden 4th one. The key is, across all 4 dimensions, energy is still perfectly conserved.
So the whole hypothesis is really built around a single, elegant equation that combines 3 core ideas. First, you've got your standard wave motion, how things move around. Second, you add a damping term. This represents that energy leak, and that is the time force itself. And third, there's a self-interaction term, which is crucial because it allows stable things, like particles, to actually form and hold their shape, instead of just dissolving away into that 4th dimension. Okay, so the theory gives us a potential mechanism for the arrow of time and the expansion of the universe. But this is where it gets really, really elegant. The framework doesn't just explain time. It also seems to explain quantization, almost like an accidental and incredible side effect.
You see, the theory is built on this principle of perfect equilibrium. So the energy flowing into our 3D brain has to be perfectly balanced by the energy leaking out. When this condition is met, which mathematically is described as J equals 0, something amazing happens. The whole system just naturally settles into discrete, stable states. You don't have to force quantization on it as a rule. The system quantizes itself. It just spits out a specific spectrum of particle masses, all from this one simple balancing act.
And honestly, this is the big payoff. In standard quantum mechanics, we basically just say, well, the universe is quantized because it just is. We have to bake it into the rules from the start. But here, quantization just emerges naturally from the geometry of a 4D space and this principle of equilibrium. It's a result, not an assumption. That's a huge deal.
Now, this is all fascinating speculation, right? But is it actually science? Well, the real strength of the time force hypothesis is that it's not just a cool story. It makes specific, concrete predictions that we can actually go out and test. That means it can be proven, or maybe more importantly, it can be disproven.
The theory makes 4 totally distinct testable predictions, and they're across an incredible range of scales. First, it predicts a new particle should pop up at the Large Hadron Collider. Second, it predicts a tiny constant noise, or jitter, that should be detectable by our most sensitive atom interferometers. Third, it predicts that the redshift of distant galaxies should actually change over time in a very specific way. And fourth, it predicts an incredibly faint effect on gravitational waves. So you have 4 different tests, from the tiniest subatomic scales all the way up to the cosmic.
Now, in particle physics, you don't just find something. You have to be absolutely, positively sure. The gold standard for any discovery is called 5 sigma, or 5 sigma. What that means is there's only about a 1 in 3.5 million chance that what you saw was just a random fluke. It's the benchmark for saying, okay, we've found something real.
And this is what makes the time force hypothesis such a powerful scientific proposal. The authors state crystal clear that if any one of those 4 predictions is tested and the result is off by more than 5 sigma, the entire framework is wrong. Refuted. It's a bold, all-or-nothing proposition. You gotta respect that.
So we're left with this one profound question. Could it really be that the most fundamental experience of our lives, this relentless one-way flow of time, is just a shadow, the observable signature of our entire universe, just trying to find balance in a grander 4-dimensional space that we can never, ever directly see? You know, only time and our experiments will tell.